If you've ever worked with wireless-enabled devices, you know troubleshooting issues in both the time and frequency domain can be frustrating and time-consuming. One of the biggest challenges is viewing analog or digital signals on an oscilloscope time-aligned with your RF signals on a spectrum analyzer. In the next few minutes, you will see how easy testing can be with the MDO4000 series mixed domain oscilloscopes. The MDO4000 series provides you with time-correlated acquisition of analog, digital, and RF signals for tracking down system-level issues quickly and efficiently. For the first time ever, you can easily see the time domain and frequency domain in a single instrument, all correlated in time. For optimal performance, the MDO has an RF input with dedicated RF hardware. Once a signal is connected to this port, and with just a few button pushes, you can see the RF spectrum of the signal, time-aligned with your other signals. At this point, you can use any of the MDO's 125 different trigger combinations to acquire your signals of interest. When the trigger event occurs, all of your analog, digital, and RF signals will be acquired simultaneously for further analysis. With the MDO, you can view your RF spectrum at any point in time in your acquisition. This orange bar, called the spectrum time indicator, shows the location in time of the data that is being used to generate the spectrum display of your RF signal. You can move its position by using the intuitive wave inspector control. As the spectrum time indicator moves in time, the spectrum is updated automatically. Now let's look at an example of a phase lock loop, or PLL, as the frequency is tuned. Here's a setup for this example. On channel 1, VCO enable line is probed and channel 2 is connected to the PLL voltage signal. The SPI control bus is monitored using the digital inputs on the MDO. The PLL output is connected directly to the RF input. What happens first is the SPI bus sends a command to the VCO to be set from 2.2 to 2.4 GHz. Based on the command received, the PLL output voltage increases as expected. This higher voltage then tunes the VCO to a proportional frequency. After some time delay, the PLL output frequency adjusts to proper frequency. As spectrum time is moved, you can see the spectrum tone increasing and finally settling at 2.4 GHz. The spectrum of the PLL output is easily seen before the command to change frequency, during the change, and after the PLL settles. This single instrument allowed us not only to view serial bus commands and analog outputs, but also quickly analyze the turn-on time of a PLL. Let's look at another example, a wireless-controlled servo motor. The goal is to measure the time delay in the system from when the motor control signal is received and the RF signal reaches its new state. Here, the center frequency is set to 75.45 MHz to match the transmitter carrier frequency. To view how the RF signal varies over time, the RF amplitude versus time trace is added in the time domain view. Next, the MDO will use an RF pulse width trigger to capture the command. Pressing single sets the scope up to save the first instance of the trigger. As you can see, both the RF signal and corresponding servo control signal were captured in the same acquisition. Using the cursors, you can quickly measure the time delay between the RF signal and control signal. As you've seen, correlating events in the frequency domain with time domain signals is straightforward and simple with the right tools. Whether you're integrating Bluetooth, Zigbee, or other wireless technologies in your design, you can count on the MDO4000 series to help you quickly troubleshoot system-level issues.